wave lovers. Come back to Wave Essentials on GNET. Today, we are getting into the cool stuff of wave dynamics, diving into the awesome world of superposition, standing waves, and beats. In this third video, we are checking out the magic that happen when waves come together to make super cool patterns. We will watch how standing waves do their elegant dance and feel the beat of the rhythm of the waves. Superposition. We are exploring the dance of wave. Wave 1 in red and wave 2 grooving with a twist. A phase difference phi. When they team up, it is like a superheroes combining powers, creating a third wave with more power. Armed with trigonometric identities, we will unlock the hidden secrets and make problem solving a breeze. Curious minds, picture this. Information enters one ear, take a little journey inside your brilliant brain, and then whoosh. It seamlessly travels out from the other ear, making room for new discoveries. Now, grab those notebooks ready to roll into this adventure. Let's go. Superposition. When two waves travel together in a material, each wave moves separately. The combined movement of the waves at any point and time is the total result of adding up the individual movement of each wave. Imagine two simple up and down waves with the same speed going in the same direction. If we call the size of the waves as A1 and A2, and their starting point are a bit different, represented by symbol phi, then their position at any moment can be expressed as: for wave 1, y1 a1 sine omega t, and for wave 2, y2 is equal to a2 sine omega t plus phi. According to the principle that we can add the waves together, that is superposition, the total displacement is the sum of the displacements of the two waves. Therefore, y is equal to y1 plus y2 equals to a1 sine omega t plus a2 sine omega t plus phi. We can simplify this expression using trigonometric identity. Sine of x plus y is equal to sine of x into cos of y plus cos of x into sine of y. By applying this identity, y is equal to a1 sine omega t plus a2 into bracket sine of omega t into cos of y plus cos of omega t into sine of y bracket close. On further simplification, we get y is equal to into bracket a1 plus a2 cos of phi bracket close into sine of omega t plus a2 sine of phi into cos of omega t, equation 1. Let's introduce a constant a and theta such that a1 plus a2 cos of phi is equal to a cos theta, equation 2. a2 sin phi is equal to a sin theta, equation 3. Substituting equation 2 and 3 in equation 1, we get y is equal to a sin omega t into cos of theta plus a cos omega t into sin theta. It can be written as y is equal to a sin of omega t plus theta, equation 4. The equation we have derived is y is equal to a sin into bracket omega t plus theta, bracket close. Note, the interference of the two waves produces a progressive wave with the same frequency as the mixing waves. However, the phase is different from that of the mixing waves. Now, we will calculate the amplitude of resultant wave and phase theta. Squaring equation number 2, that is a1 plus a2 cos of phi is equal to a cos theta, we get into bracket a cos of theta bracket complete raised to 2 is equal to into bracket a1 plus a2 cos of phi bracket complete raised to 2. Squaring equation 3, that was a2 sine of phi is equal to a sine theta. On squaring, we get into bracket a sine theta bracket close raised to 2 is equal to into bracket a2 sine phi bracket close raised to 2. Adding above two equations, we get s square sine square theta plus s square cos square theta is equal to a2 square sine square phi plus into bracket a1 plus a2 cos of phi bracket close raised to 2. What equation we have got is s square sine square theta plus s square cos square theta is equal to a2 square sine square phi plus into bracket a1 plus a2 cos of phi bracket close raised to 2. Now, simplifying it further, we get s square into bracket sine square theta plus cos square theta bracket close is equal to a2 square sine square phi plus a1 square plus 2 times of a1 a2 cos of phi plus a2 square cos square phi. Since sine square theta plus cos square theta is equal to 1, we get a square plus a1 square plus a2 square into bracket sine square phi plus cos square phi bracket close plus 2 times of a1 a2 cos of phi. On simplifying it, we get a square plus a1 square plus a2 square plus 2 times of a1 a2 cos of phi, and the resultant amplitude is a equals to under root of a1 square plus a2 square plus 2 times of a1 a2 cos of phi. Here phi is the phase difference between the two waves, and phase of the resultant wave is tan of theta is equal to a2 sine phi divided by a1 plus a2 cos of phi. Thus, when two waves travels in a medium simultaneously representing the separate motions, the resultant displacement at any point and time is the vector sum of the individual displacement. We know that intensity is directly proportional to the square of the amplitude. It is I is proportional to a square. Therefore, I is proportional to into bracket a1 square plus a2 square plus 2 times of a1 a2 cos of phi bracket complete. The resultant amplitude A is maximum when cos of phi is equal to 1 or phi is equal to 2 pi m, where m is an integer. It is therefore I maximum is proportional to into bracket a1 plus a2 bracket close raised to 2. The resultant amplitude A is minimum when cos of phi is equal to minus 1 or phi is equal to into bracket 2m plus 1 bracket close into pi. Therefore, I minimum is proportional to into bracket a1 minus a2 bracket close raised to 2. We will study formation of stationary waves. When two waves with the same amplitude and wavelength travels in opposite directions along a straight line and overlap, they create what we call a stationary waves, also known as standing waves. We will study the characteristics of stationary wave. Stationary form. Unlike traveling waves, the shape of stationary wave remains fixed in space, giving the appearance of a stationary pattern. Nodes and antinodes occur alternately along the wave. Nodes are points with zero displacement, while antinodes have maximum displacement. Third, displacement at the nodes and antinodes. At nodes, the displacement is zero, and at antinodes, it is maximum. This creates a distinct pattern of highs and lows in the waves. Pressure changes. Maximum pressure changes occurs at nodes, while minimum pressure changes happens at antinodes. Particle motion. Except all nodes, all particles undergoes simple harmonic motion with the same period. Amplitude variation. The amplitude of a particle displacement is not uniform. It is highest at antinodes, gracefully decreasing and reaching to zero at nodes. Particle velocity. Particle velocity is zero at nodes, gradually increasing and reaching maximum at antinodes. Distance between nodes and antinodes. The distance between the consecutive nodes and antinodes is equal to half the wavelength lambda by 2, while the distance between the node and its adjacent antinode is equal to 1/4 of wavelength lambda by 4. Energy transfer. Unlike traveling waves, stationary waves do not transfer energy. All the particles pass through their mean position simultaneously twice during each vibration. Phase relationship. Particles with the same segment vibrate in the same phase, while the neighboring segments vibrate in opposite phases, contributing to the stationary nature of the waves. Now, let's dive into the analytical realm and unveil the mathematical magic that describes these waves. Analytical method. Imagine a wave moving along x-axis with amplitude a and wavelength lambda. Let its equation be y1 is equal to a sine into bracket kx minus omega t bracket close. Another wave travels in opposite direction. Its equation be y2 is equal to a sine into bracket kx plus omega t bracket close. Wave y2 is moving along negative x-axis without phase change, or phi is equal to 0. According to the principle of superposition, adding these two waves gives the resultant displacement y is equal to y1 plus y2. Therefore, we get y is equal to a into bracket kx minus omega t bracket close plus a sine into bracket kx plus omega t bracket close. The equation what we have obtained is y is equal to a sine into bracket kx minus omega t bracket close plus a sine into bracket kx plus omega t bracket close. If we consider x is equal to kx and y is equal to omega t, then by applying the trigonometric identity, we can simplify it further. Trigonometric identity is sine of x plus y plus sine of x minus y equals to 2 times of sine of x into cos of y. Therefore, after applying this identity, we get y is equal to 2a sine of kx into cos of omega t. This equation describes a stationary wave y is equal to 2a sine kx into cos omega t. On substituting the value of k and omega, we get the equation as y is equal to 2a sine of 2 pi upon lambda into x into cos of 2 pi upon capital T into small t. Sine term 2a sine of into bracket 2 pi upon lambda into x. The term does not involve time. Wavelength lambda is fixed. X indicates the position of the particle along the wave. Particle oscillates between plus or minus of 2a. Cos term cos of into bracket 2 pi upon capital T into t bracket close determines the exact displacement of a particle at a specific position x over time t. Describes the up and down motion along y-axis. Note that the frequency of a standing wave is equal to the frequency of superposing waves. Location of nodes. For node condition, amplitude should be 0. Therefore, sine of into bracket 2 pi upon lambda into x bracket close should be equal to 0. This condition can be achieved if 2 pi upon lambda into x is equal to 0 or pi or 2 pi or so on. Therefore, 2 pi upon lambda into x equals to n pi. On simplifying the equation for x, we get x is equal to n lambda by 2. Therefore, at x is equal to 0, lambda by 2, lambda, 3 lambda by 2, amplitude will be 0. The distance between the two consecutive nodes is lambda by 2. Antinode. Condition for antinode is if sine of into bracket 2 pi upon lambda into x bracket close is equal to 1, then maximum amplitude will be plus or minus 2a. For points of maximum displacement, 2 pi upon lambda into x should have the value of pi by 2 or 3 pi by 2, etc. Therefore, we can summarize it as 2 pi upon lambda into x equal to into bracket 2n minus 1 into pi divided by 2. Here, n is equal to 1, 2, 3, etc. On simplifying the equation for x, we get x is equal to into bracket 2n minus 1 bracket close into lambda divided by 4. We get the position of antinode as x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. Distance between the two consecutive nodes is lambda by 2. In summary, stationary waves exhibit a unique pattern where nodes and antinodes are arranged alternately, creating a fixed waveform with distinct characteristics of displacement, pressure, and particle motion. These waves do not transfer energy and showcase a specific phase relationship amongst neighboring segments. Beats. Beat formation when two waves of nearly equal frequencies travel in a medium along the same direction and superimpose upon each other, beats are produced. It got following characteristics. Amplitude variation. The amplitude of the resultant sound at a point rises and falls regularly due to the interference of the two waves. Intensity variation. Similarly, the intensity of the resultant sound at a point rises and falls regularly with time. Waxing and waning. When the intensity rises to a maximum, it is referred as the waxing of sound. Conversely, when the intensity falls to a minimum, it is called waning of sound. Phenomena of beats. The phenomena of waxing and waning of the sound due to the interference of the two sounds of a nearly equal frequencies is collectively referred as beats. Beat frequency. The number of beats produced per second is called the beat frequency. It is equal to the difference in the frequencies of the two waves causing the beats. Now, we will try get the mathematical equation for beats by analytical method. Let us consider two waves of slightly different frequencies omega 1 and omega 2 such that omega 1 is greater than omega 2, having equal amplitude traveling in a medium in the same direction. At time t is equal to 0, both waves travels in same phase. The equation of these two waves are y1 is equal to a sine omega 1t and y2 is equal to a sine omega 2t. With the two waves superimposed, the resultant displacement is given by y is equal to y1 plus y2. Therefore, y is equal to a sine omega 1t plus a sine omega 2t. Now we will use the trigonometric identity to simplify the equation. Sin x plus sin y is equal to 2 times of sine of x plus y divided by 2 into cos of x minus y divided by 2. Therefore, we get the equation of y as y is equal to 2 times of sine of into bracket omega 1 plus omega 2 divided by 2 bracket close into t into cos of into bracket omega 1 minus omega 2 divided by 2 bracket close into t. The equation just what we have derived is y is equal to 2 times of sine of into bracket omega 1 plus omega 2 divided by 2 bracket close into t into cos of into bracket omega 1 minus omega 2 divided by 2 bracket close into t. If omega a is equal to omega 1 plus omega 2 divided by 2 and omega b is equal to omega 1 minus omega 2 divided by 2, then equation can be rewritten as y is equal to 2 sine omega a t into cos of omega b into t. The term sine omega a t influences the amplitude of the interference pattern governing the loudness or the intensity of the beats. Term cos of omega bt influences the rate of interference determining the speed at which the beats occur, that is beat frequency. Beat frequency formula. Beat frequency is given by the difference in the frequencies between the two original waves. Therefore, n beats is equal to modulus of n1 minus n2. Now, buckle up your problem solving hats, gather those notes we have taken while learning, and let's shift from theory to practice. Get ready to apply what you have learned and embrace the excitement of solving numerical puzzle. In this given problem, wave is not propagating but standing, as sine and cos terms are in multiplication, but sine and cos has switched their position. So cos of into bracket 0.01x bracket close will be the part of an amplitude, while in our standard equation it is sine of kx. So k is equal to 0.01 and omega is equal to 100. From the formula of wave velocity, v is equal to omega upon k. Substituting the values of omega as 100 and k as 0.01 and simplifying it, we get 10 raised to 4 meter per second. Option A is correct. This question is, a standing wave having 3 nodes and 2 antinodes is formed between the two atoms having a distance 1.21 angstrom between them. Asked to find out wavelength of the standing wave. The distance between the node and antinode is lambda by 4. Therefore, 3 nodes and 2 antinodes are formed in a distance of lambda. Therefore, lambda will be 1.21. Option A is correct. In this question, the wave equation is not in the form of standing wave as they are not traveling in opposite direction. So, waves will add vectorially to give new propagating wave. Amplitude of such interference or mixing of wave is given by S square equal to A1 square plus A2 square plus 2 times of A1 A2 cos of phi. Here phi is the phase difference. It is given that A1 is equal to A2 is equal to A and A is equal to A. Therefore, A square plus S square plus S square plus 2 times of S square into cos of phi, which implies that cos of phi is equal to minus 1 by 2. Therefore, phi should be equal to 120 degrees or 2 pi by 3. As stated earlier, phi denote the phase difference. Therefore, phi 1 minus phi 2 is equal to 2 by 3. Option B is correct. In this question, two sound waves with wavelength 5 meter and 5.5 meter respectively each propagate in a gas with a velocity 330 meters per second. Asked to find out number of beats per second. We will use the formula for the velocity of a sound wave, which is v is equal to n into lambda, where n is the frequency. Therefore, n equal to v upon lambda. For first wave, n1 is equal to 330 divided by 5 is equal to 66. For second wave, n2 is equal to 330 divided by 5.5 equal to 60. Therefore, beats is equal to modulus of n1 minus n2 equals to 66 minus 60 is equal to 6 beats per second. In this question, tuning fork makes 4 beats per second with the string of piano, and when the string tension is increased, number of beats decreases to 2. It means on increasing the tension, frequency of the string increases. Keeping it in mind, we will solve problem. Let n be the frequency of the piano string. Now, if n is greater than 512, then n is equal to 512 plus 4 equals to 516 Hz. If n is less than 512, then n is equal to 512 minus 4 is equal to 508 Hz. So, out of 508 Hz and 516 Hz, 1 is correct. Let's take a case 1. 516 Hz. So, after tightening the string, new frequency of a piano string becomes 516 plus 2 is equal to 518. Then, number of the beats produced should be now 518 minus 512 is equal to 6 beats per second. This contradicts the actual calculation of 4 beats as given in the problem. Case 2. 508 Hz. After tightening the string, new frequency of the piano becomes 508 plus 2 is equal to 510 Hz. Number of the beats produced will be 510 minus 512 is equal to 2, which is observed. So, original frequency is 508. Correct option is D. In this problem, two vibrating tuning forks produce progressive waves given by equation y1 is equal to 4 sine 500 pi t and y2 is equal to 2 into sine of 506 pi t. Asked to find out the number of the beats produced per minute. Now it is given that omega 1 is equal to 500 pi. The formula for the omega is omega 1 is equal to 2 pi n1, which is equal to 500 pi. Therefore, n1 is equal to 250 Hz. The second frequency is omega 2 is equal to 506 pi. Formula for omega 2 will be equal to 2 pi n2, which is equal to 506 pi. On simplifying, we get n2 is equal to 253 Hz. Thus, beats produced is equal to modulus of n1 minus n2 equal to 250 minus 253 equals to 3 beats per second. Asked for per minute, therefore 3 into 60 is equal to 180 beats per minute. Option B is correct. In this question, 3 sound waves of equal amplitude have frequencies n-1, n and n plus 1. They superimpose to give the beats. Asked to calculate beats produced per second. Since the given frequencies are consecutive, we can directly take the difference between the first and the third frequency. Therefore, beats is equal to into modulus n minus 1 minus n minus 1 equal to 2. Thus, option D is correct. In this question, a guitar, two strings A and B made of same material are slightly out of tune and produces the beats of frequency 6 Hz. When the tension in B is slightly decreased, the beat frequency increased to 7 Hz. If the frequency of A is 530, the original frequency of B will be. Now, number of beats are 6 Hz. Thus, two possible frequencies of string B, that is 530 plus 6 is equal to 536 Hz and 530 minus 6 is equal to 524 Hz. Therefore, n is equal to 524 and 536. It is given when tension in string B is slightly decreased, the beat frequency increased to 7 Hz. So we can say that frequency decreases by 1 after decreasing the tension. If n is equal to 536, so new frequency will be 536 minus 1 is equal to 535 Hz. Beats produced will be modulus of 530 minus 535 equals to 5, which contradicts with what observed is 7 beats. If we take n is equal to 524, then new frequency will be 524 minus 1 equal to 523 Hz. Then the beats produced will be modulus of 530 minus 523 equals to 7 beats, which in accordance with observed. So, n is equal to 523 is a correct frequency. Option C is correct. In this question, a stretch string is vibrating according to this equation y is equal to 5 sine into bracket pi x upon 2 bracket close into cos of 40 pi t, where y and x are in centimeter and t in second. Asked to find out the distance between the consecutive nodes of the string. Standard equation for standing wave is y is equal to 2a sine of kx into cos of omega t. Comparing the given equation with standard equation, we get k is equal to pi by 2. Since k is equal to 2 pi upon lambda, therefore 2 pi upon lambda is equal to pi by 2. On simplifying it for lambda, we get lambda is equal to 4 centimeters. The distance between the two consecutive nodes is given by lambda by 2. Therefore, 4 by 2 equals to 2 centimeters. Option D is correct. As we conclude our exploration into the captivating world of waves, we have delved into the intricacies of standing waves and beats. In our next video, get ready for an exciting journey as we venture into the realm of strings and the mesmerizing melodies of open and closed organ pipe. So, stay tuned, keep the curiosity alive, and let us continue our wave adventure together. I, Avinash, signing off. Before I leave, don't forget to like, subscribe, and hit the notification bell to stay updated on our upcoming videos. Until then, keep riding the wave of curiosity